Okay, so welcome everyone. My name is Aisha Tamour. I'm currently a climate-based fellow, and through this program, we're inviting Andre to present this talk. To quickly introduce Andre, he's a senior scientist at Aquante hydrosphere analytics with a background in climate modeling. His main interests are in seasonal hydroclimate forecasting and long-term climate change impacts on water resources using physics-based numerical and machine learning models. While overseeing weather and climate data processing at Aquante, he also leads projects focused on developing new forecasting capabilities within Aquante, either as internal research projects or in collaboration with academic partners. Examples of current projects include seasonal drought forecasting, streamflow forecasting using machine learning, and modeling regional climate change over Canada using weather research forecasting. He's originally from Germany, and he completed an equivalent of master's in dynamical meteorology in Maine before moving to Canada to complete his PhD in regional climate modeling at the physics department in Toronto. He's currently located in Kitchener-Waterloo, and he likes the outdoors, including biking and canoeing and all that good stuff. So thank you so much, Andre and Aquante, for being willingness to participate, and I'm really looking forward to the talk. The talk is going to be around 30 to 40 minutes, and maybe after that we can have some questions. So feel free to put them in the chat box.
Yeah. So probably more like 40 minutes, 45 minutes, but yeah, I tend to ramble on a bit. Okay, so you've already seen that we've had a little poll about where folks are from. We actually have a few polls throughout the talk. My colleague Braden will activate them at certain slides, and I hope I don't just plow over them. The first poll question is already there, and basically I don't really know what the audience here is. I normally talk to very technical people, but I think this is a more general audience, and so it would be really helpful for me to get some feedback on what your backgrounds are, just very roughly. So would be great if you could just type that into the poll, and there should be a word cloud appearing at some point. Okay. Nevertheless, I will just start. And so the outline for this talk, essentially, in the beginning, I'll have to introduce some basic concept in hydrology and also sort of motivate why we care about flood and drought forecasting. Then I will talk a bit about weather forecasting, because that is actually a very important component of this, and weather drives a lot of the hydrology, right? And I'll talk about current methods for forecasting. Then I'll get to sort of the sexy part, the machine learning. A bit about the not really the theory of the machine learning techniques, but why a particular approach works and others before have not worked. And I'll talk a bit about the data sets and the skill of the models and the training, and a few sort of interesting things we've learned. Just by the way, for the polls, you should be able to just enter your answer to the poll in the poll window. If you don't close it, you may be able to open it also from the comments tab as well. I'm not entirely sure about that. Okay. Yeah, and the last part is actually maybe the most interesting one, and that is how we went from theory, from what has been published in the academic literature, to implementing this in practice as a service that we run operationally. And that is not that easy. Okay, so let's get started. A bit of background. So a lot of the impacts of climate change are mediated through water resources, and the extreme ends of this are drought and flood, right? And these are very intricately linked to food security and also human health, through water quality, for example, but also just a physical risk from flooding, especially. So, and how we manage these resources, and if we can manage them sustainably, steers us in a particular direction, right? And so we want to go into the right direction towards a sustainable future, and if possible, avoid the worst outcomes of a drought and flood. Um, and at the moment, we are not very good at sustainably managing water resources. So especially when it comes to irrigation and groundwater, we do a lot of our agriculture in relatively dry subtropical climates where we use surface water and also groundwater for irrigation. And in many cases, especially the use of groundwater is not sustainable. And there's so this has major implications for food security. Droughts are major drivers of crop losses and are in most parts of the world probably the most expensive or economically damaging natural disaster. The only exception to this, I think, can be earthquakes and in some regions, tropical storms. Um, in order to sustainably manage water resources, we have to understand them better. We also have to regulate them a lot better. This is also a very big question for policymakers. At the moment, water resource regulation is very outdated, usually based on regulation that was passed 100 years ago, when usage and also available resources were very different, and our understanding was not nearly as advanced as it is now. And one term I want to just throw out there, um, groundwater mining, right? Um, this is that a lot of the use of groundwater is actually mining, in the sense that fossil groundwater is pumped up from the ground, and this is not renewable. This is not recharged. This is water that's stored underground, and we're just removing it, and it's going to be used up in a few decades in many cases. So yeah, the economic impacts are very, very large. With climate change, flooding and storms become more common, partly because of increasing rainfall and just more severe weather, but also because of population growth and our exposure just increases. So there's more built up now in areas that are flood prone because there's just more development, and all the not flood prone areas have already been developed, right? And so a lot of this is pushed into floodplains, and this is very dangerous. And that, of course, leads to large insurance claims. And so here on the right-hand side, so damages over time have increased significantly, so almost a factor of 10 in 20 years. Yeah. Okay. So this is the motivation here. So forecasting this would be really helpful. And there are, of course, large governmental organizations and also intergovernmental organizations that really work on this and have the mandate to monitor flood and drought situations. Especially drought is basically continuously monitored in North America because it's a more slow-moving phenomenon, right? Um, and forecasting would be really useful to prepare and mitigate. But also, of course, current monitoring is very helpful for this as well. And this is the North American drought monitor that I have up here. And this is the current drought situation in North America. So they publish this monthly. This is from March. They should have the April assessment out in a few days. And you can see that, for example, southern US and Mexico are under severe drought conditions at the moment. And also Western Canada. Everybody who lives in Canada, I live in Canada, and so we actually work with people from the government in Alberta on this drought situation. Yeah, it's very severe. It's already the second year of drought, so these multi-year drought situations are a real problem, becoming a bigger problem. At the moment, these government agencies provide information, but primarily so gathering or collecting information, and they provide outlooks. The forecasting of drought is its infancy at the moment, and hydrological forecasting in general over longer timescales. So there's a lot of opportunity here because the economic value is obvious and is extremely large. All right. So before we continue, I think I'll introduce a few basics about the hydrological cycle, because flood and drought are essentially just the extreme ends of the same sort of set of processes, right? And there's also a new poll question here, what you would be most interested in, what kind of events. So if you have a view on this, if there's something that relates to your professional practice, maybe just select something here. Yeah, so the hydrological cycle, or the water cycle, as it is also often called, is mostly seen in the form of precipitation, and then of course stream flow. But it starts in the oceans where most of the water is, right? And solar radiation, so sunlight, really drives evaporation from water surfaces, which then rises into the atmosphere, forms cloud, forms precipitation over land and also over the ocean. But over the ocean, it just goes back into the ocean. So over land, you get precipitation, especially in areas where there's topography, so mountain ranges. You get a lot of precipitation there because the air is forced to rise over, and then you get condensation. One thing that a lot of people don't really realize is that actually about 70% of the rain and snow that falls on the continents actually re-evaporates. And then it may fall again over the continent, or it may fall over the ocean. But evaporation is a very significant part of the water cycle, also over land. The part that does not evaporate, it runs off or infiltrates. So infiltration leads to groundwater, and then a lot of the groundwater actually collects also at streams and then upwells in the stream bed and forms base flow in streams. And then there's of course also a lot of surface runoff. So after a heavy precipitation event, or when there's a lot of snow melt, water collects in small streams, and then these collect into bigger streams, and then they form large rivers, right? And this is surface runoff. And so we mostly look at surface runoff and groundwater indirectly, usually because when it contributes to surface runoff. But of course, when you're pumping groundwater, then we also want to look at groundwater directly. So important concepts: evaporation and precipitation, runoff, that's on the surface, groundwater, and then of course also snowfall. So a lot of precipitation falls in the mountains and in winter, and then it falls as snow. And so it does not directly contribute to stream flow. And it melts in spring. So this is a nice picture of mountains and snow. So what typically happens then is, as it gets warmer in spring or even in early summer, the snow melts. And then you get a strong runoff peak in late spring, or depending on how far north you are or high up in the elevation you are. This is a typical sort of average what we call hydrograph. So this is a stream flow on the y-axis, and then the day of the year on the x-axis. So in late spring, early summer, you get a large peak in this in stream flow. It can be like 5 times as high as the average flow. The variability is really large there, and this is in the South Saskatchewan. So this is in Alberta in Canada. And of course, because of the Rocky Mountains, this peak is relatively late, and it's relatively far north. So often this is a little bit earlier. And if you don't have as much topography, then the peak is not as high, right? But this is a very important effect, and this is also called a spring freshet. Very important to realize is also the fact that this kind of snowmelt-driven runoff behavior is really sensitive to climate change. So with warmer temperatures, you can expect this peak to move earlier into the season. So what we see in climate projections about a month earlier. But what can also happen is that in some regions where you have ephemeral snow cover, it's snow dominated, but there's already a lot of rain in winter as well. So actually in southern Ontario, you have that situation. Um, what can happen is that it gets too warm for snow to really become persistent in winter. And then you get a lot of snowmelt events in winter and also a lot of precipitation that falls as rain. And then the watershed actually shifts from snow dominated to rain dominated. And the hydrologic behavior changes completely, right? So this is a very important potential impact of climate change. It can completely change the seasonal cycle of runoff, right? And that really depends on where you are and what the runoff dynamics in the watershed are. Okay. And this is another hydrograph, this time not an average one, but it's the same South Saskatchewan River in Alberta, but different years in succession. And just what I want to highlight here is that the variability between years can be really large. So 2001 was a relatively dry year, but then 2002 has a really, really large flood. So this is called a hydrograph, and that's basically what we're trying to predict with our machine learning models. And so I just want to put this out early, like that you know what we're talking about. The machine learning models are actually going to predict this time series of discharge, so cubic meters per second of water that's coming down a river over time. Okay, and yeah, there's a lot of variability year to year, and if you were able to predict this, there would be a lot of value in this, because then we would know if you need to fill reservoirs, if it's going to be a dry year, or if you need to empty reservoirs, if there's going to be a flood, right? So this is very important. Okay. Now, for forecasting, this is our conceptual diagram of what are the pieces that you actually need for environmental forecasting or hydrological forecasting, right? And so you need a weather forecast. This is really important, and in a minute I'll spend some time talking about weather forecasts. So the hydrological response is really driven by weather and climate. So this is the first step to predicting hydrology, is to predict the weather. Then you also need to know the physical characteristics of your watershed. That's also very important. So slope, for example, is extremely important in terms of runoff dynamics. If it's steep terrain, you get fairly quick runoff, right? If it's very flat, you get a lot of pooling of water, and then as a consequence, a lot of evaporation. Depending on what the soils are, you get more or less infiltration. And for example, in urban environments, you get very little infiltration. Land cover is very important. Yeah, and so then you kind of have to integrate that into your model. You have to build a model that takes weather forecasts as an input. It accounts for all of these characteristics of the watershed, and then you can produce a forecast. And the forecast is going to be some kind of hydrograph, some kind of line that tells you the discharge over time, right? Okay. So that's sort of the conceptual background. Now, numerical weather prediction. And so most folks are familiar with the weather prediction you get on your phone, right? But that's not really useful for hydrological forecasting. It just tells you it's going to rain. It doesn't even really tell you how much it's going to rain, right? Sometimes they do, sometimes they don't. But there's actually a huge and very sophisticated enterprise behind this. It's probably the largest sort of environmental prediction enterprise and the oldest that is around, and it's global. So the World Meteorological Organization actually coordinates a large network of weather stations and satellites and aircraft and ships that observe the weather, and they collect the data all around the globe. And amazingly, all nations collaborate on this. So this even includes Russia, even at the present day. We do get weather observations from Siberia, for example. And we also, of course, share our weather observations with them. And this is done by national centers that collaborate through these international organizations, and they share data and they run forecasts. And these forecasts are based on physical models. So these are essentially sort of like engineering type models, very similar to what you would use in aerospace, for example, to compute the flow around an airfoil or something. These models are very similar in the sense that they compute the currents of the air in the atmosphere and the thermodynamics and solar radiation and snow accumulation and sea ice and things like that. They are very similar to climate models. Some people may be more familiar with climate models. So weather and climate models are essentially the same thing. Climate models typically run at coarser resolution because they run much longer timescales, and they emphasize different processes more, so more biogeochemical processes like carbon cycle, for example, which weather models don't do, because the carbon cycle is not important over a 2-week time span, right? Yeah. There are, of course, also now machine learning approaches to this, but that's an entirely different topic. And these run on supercomputers. So the output that they generate looks something like this, right? So this is a map, a gridded map of precipitation, in this case over Europe, generated by a weather prediction model, a numerical weather prediction model. So you can see all these like swirls and eddies, and like, this is all driven by air currents and humidity and thermodynamics. And global weather forecasts run for about 2 weeks into the future. And then most national centers also run high resolution regional forecasts that run for 2 or 3 days. And you may have noticed that these 2 to 3 day forecasts are actually usually pretty good. And so they run very high resolution, and yeah, they tend to be pretty good. The 2-week forecasts are useful, but they often have large errors. So they are more useful in a probabilistic sense, not in a deterministic sense. And yeah, so we have another question here for you. Yeah, how do you value the communication of uncertainty in a weather forecast or a hydrological forecast? So these days, weather services are actually pretty good about communicating that even to end users with like percentage chance of precipitation, for example. But there are, of course, more sophisticated ways of doing this for technical users. And the weather forecast data, these are actually these are gridded fields of binary data, and these can be very large. And then the weather company, for example, they just grab this, they download this from the National Weather Service, and then they run some statistical analysis on it and translate it into these funny little icons you see on your phone, right? But they actually pull these binary data, and this is what we do too. And so for our machine learning forecast, that's what we have to do as well. And this is actually very specific and very technical. So you need a lot of expertise and knowledge in this domain to actually work with this weather forecast data. Not trivial at all. So I would highly recommend to work with somebody who has a background in atmospheric science and meteorology, if this is something that you want to approach. Okay. Now, how do we model streamflow then, right? So weather forecasts are done with these really huge physical models. Streamflow is actually done in a different way usually. And this is called rainfall runoff modeling. So we get the rainfall, and this can be historically observed rainfall from a rain gauge, or it can be from a weather forecast, right? And then, so in this cartoon here, you get some rainfall, and then typically with some delay, you generate a flow response in the stream, right? And so the way that these rainfall runoff models work is they take the precipitation input, and then they sort of have different buckets where they allocate the water, and then they store it for a time, and then they release the water with a release coefficient. And if the temperature is below 0 degrees, for example, they would just put it into a snow bucket, and then once the temperature rises above 0 degrees, they have a melt rate at which they then deplete the snow bucket and push the water into the stream. Then they have an evaporation loss coefficient or something like that. And this is all sort of semi-physical, like there's a physical explanation for it, but it's not really physical in the sense that these are all just tunable parameters. And so you have to calibrate those. And the way that this is done is you just take the precipitation input and also other climate variables like temperature or solar radiation, and then you take the desired output, so the stream flow, and this actually has to come from measured stream flow, so a stream gauge, and then you adjust methodically the parameters in the model with an optimization algorithm until you you get a good forecast, or until you get the right relationship over the historical time period between the weather input and then the resulting stream flow. Essentially a calibration process or an optimization process. This is very data-driven in a way, or statistical almost. But if you have a long enough streamflow record and the weather record in your watershed, this actually works really well. And most operational forecasting is done this way at the moment. The main limitation of this is that this is impossible to do if you do not have a long enough streamflow record or weather record. Yeah? So this is the major limitation. But this is how this is done today. This is data-driven and in many ways very similar to machine learning, but way older. This has been done since like the 60s. Like with the very first computers, people have started doing this. Okay. So then operationally, this is, for example, a similar process, which is a little bit more physics-based, is implemented with the National Water Model in the US. So in the US, they have streamflow forecasting capability based on a sort of semi-physical approach. It's a slightly different than what I've just outlined. That was very sort of statistical. This is a little bit more physical, but they have this over all the major streams in the United States. In Canada, we actually don't have that, but Aquanti does have a real-time forecasting platform that we have deployed in some regions. So it's called HGS Real-Time, and I just want to point out that like, in Canada, we have this, like the National Water Model is not the only game in town here. But this is based on a physical model, and it's a very, very far on the physics side. But the drawback of this, so the model is called HydroGeosphere. The drawback is that this model is very expensive to run and set up. So it takes a long time to configure the model. We still need to calibrate it. And then running the model actually takes hours for a single watershed. Right? So the scalability is maybe a bit limited. This is a deployment we have in Southern Ontario here. And here on the right-hand side, you can see a forecast. This is for a 32-day forecast. Also from mid-April. Yeah, and this model also forecasts groundwater, which is quite unique. The National Water Model does not forecast groundwater. But that also, again, makes it more expensive because we have to consider the entire subsurface as well. Okay, so on the spectrum of environmental models, and I really like this way of summarizing or conceptualizing models in general, and I hope this is even useful to people who are not modelers themselves. But models exist essentially on a spectrum, right? And that ranges from data-driven and machine learning models would fall onto the data-driven side on the left-hand side, and physics-based models on the right-hand side. And for example, weather prediction models fall very far on the physics-based side. They're essentially CFD, computational fluid dynamics models. They are calibrated to some extent. Weather models more so than climate models. Climate models are really entirely on the right-hand physics-based side. These models generalize very well, but they're usually very expensive to run. They need very high resolution, and they need a lot of input data usually as well. Whereas data-driven models are typically very fast to run, but they need to be calibrated. And so you need to have a good data set of exactly the thing that you want to predict. And then you have to be very careful not to do out-of-sample prediction. And yeah, so in rainfall runoff models, the current hydrological models that are used operationally are very far on the data-driven side, like machine learning models. Yeah? Okay, and the National Water Model sits somewhere in the middle, and our model is a little bit more to the right. Okay. And so with that, there's one question about how you feel about the importance of physics-based versus data-driven models. So if you have a view on that, please answer the poll question. And now I'll get to the fun part, the machine learning part. And I'll try to keep this relatively understandable and not go into too much detail here. So we've learned now what's the current method in rainfall runoff modeling and what sort of the shortcomings are, and that's that you need a streamflow record. And then, so how can we do this better with machine learning? And it's important to realize like machine learning does not always automatically work better. And sometimes what's currently being done is actually pretty good. So if you have an idea about some prediction problem or predictive analytics, look at what has been done before, because sometimes there are handcrafted methods that are actually quite good. Okay. But having said that, I've explained how rainfall runoff modeling is really very data driven. And so it's kind of obvious to try machine learning here, right? Because that's also a data driven method. And yeah, we are not the first to try this. Like, this has been done for 20 years. The only thing is, it's never really worked very well. And so typical like artificial neural networks, random forest methods, people have tried them basically as drop-in replacements for rainfall runoff models. But the models either massively overfit the training data or they have very poor performance. And the reason for this is essentially that when you're training the model, a machine learning model has to learn two things. It has to learn the model structure and it has to learn the parameters. Whereas the conceptual rainfall runoff model that has been handcrafted has a handcrafted structure that is crafted by physical understanding of the system. So it doesn't really have to learn the structure of the model. It already has a pretty good structure. It just has to learn the coefficients. And this is why it actually worked pretty well and better than the machine learning models, okay? But there was a major breakthrough about 5 years ago in this field. And this was a paper by Frédéric Kratzer et al. That introduced two major advances. One is the use of a different model architecture. So what's called an LSTM, a long-term short-term memory system. And then this is one thing, and people like to talk about fancy model architectures, and that draws a lot of attention. But that's really not, probably not even the most important thing. What's also really important is a new data set. So there's the CAMELS data set, which was published actually by the National Center for Atmospheric Research for hydrological model intercomparison and calibration. And this is a homogeneous data set with over 500 watersheds in the US that have metrology and streamflow records and physical properties associated with them. And so for the first time, it was possible to train a machine learning model on a large number of watersheds. And before, people have tried to apply them to just like one single watershed. And with this large data set, it was now possible for the machine learning model to actually learn the structure and learn a good structure, and then also learn the parameters. And then the models actually generalize quite well. So why does the LSTM, the long-term, short-term memory network, work well? The reason is, so this actually comes from natural language processing, but they've long been abandoned in natural language processing because transformers are much better. But LSTMs have a hidden state. The hidden state is essentially a memory cell. And they can use this hidden state to track the state of a system, and that means they can track the state of a watershed, which this has a real physical correspondence, right? So they can track the snowpack in the watershed. They can track the groundwater table in the watershed. If there are lakes, they can track how much water is in the lakes, things like that, right? So just from physical intuition, a model that has an internal state makes sense. And if you look at the rainfall runoff models or the physical models, they all have internal states. And previous models didn't have that. So the model structure just didn't allow the model to track the internal state. And these LSTMs do. So this was very important. And there's a physical reason for that. And then, yeah, the CAMELS data set. The CAMELS data set has about 550 watersheds across the US. in very different climate zones. It has surface cover characteristics, climate characteristics like mean elevation, slope, leaf area index, like sort of like a measure of vegetation density, right? And all averaged over the watersheds. And along with precipitation and radiation and temperature and stream flow, so that you can really calibrate your model. Okay. And so before I talk about the skill, the way you usually measure skill is NSE, so the Nash-Sutcliffe model efficiency. You don't really have to understand how it works, but it's similar to R square, but 1 is perfect and 0 is useless. So just keep that in mind. The values range from, the values can be negative, but 0, when it's 0, then the model is worthless. So, okay. And this is the skill distribution over these 500 watersheds. And the red one is basically what we want to look at. So these are the LSTMs. And 1 is here on the right-hand side, and then 0 is here. And the red line is by far the one furthest right. So it's the best performing. Other lines of note are the blue line. The blue line here is the national water model. So it doesn't actually perform that well. The machine learning model is much better. The orange line is a rainfall runoff model that's very commonly used in the US, the SAC model. And that one actually performs better than the national water model. Not by that much, but it does perform better. So with this, these models actually work really well. They generalize well between basins, and they actually learn some physics. So this is now successful. Okay, good. And before I continue, I need to acknowledge that when we implemented this, and we did, we actually took a lot of code from neural hydrology. Neural hydrology is a PyTorch package on GitHub that is essentially published by the research group that also published the Kratzert et al. Papers. They essentially just put their code on GitHub for other people to use. It has a lot of plugins for different data sets and a lot of infrastructure for testing and training, essentially rainfall runoff models. So it conceptually follows the structure of rainfall runoff models. And this really helped us a lot to get started. And when you plan a ML project, it really pays to check if whatever has been published in the scientific literature also has associated like GitHub repositories or code published, because they often do. And then often this is open source and you can actually use it. Okay. Since I'm already shouting out people, Copernicus Climate Change Services is something that I just want to highlight for anybody who wants to implement climate services or make a business out of climate data. This is a great resource. It's an EU program that really understands climate services and sort of the data needs for climate services. And they have like historical climate data sets, weather forecasts, seasonal weather forecasts, and also climate projections, right? So lots of data available. So go check that out if you're interested. And talking about climate change, one very important note about model training that I'm just throwing this in here, and I just don't want you to forget that, is when the climate is warming, precipitation patterns are changing, right? And so this on the bottom right is how the precipitation changes might occur based on the IPCC report. Keep in mind that snow-dominated watersheds may become rain-dominated. This is a major change, and that will invalidate any calibration you do with, for example, a rainfall runoff model or also a machine learning model. If you cannot demonstrate that the machine learning model works well in different climates. And this is generally true for any data-driven method, right? So this is not only streamflow forecasting, any kind of environmental prediction, if you train it on historical data, you have to think very hard about whether this is going to be valid in the future. Okay. And the more physics you can incorporate into your prediction, the more robust it is going to be. And you really need to investigate how well this generalizes. Yeah? The LSTM models, as it turns out, actually generalize quite well. Okay, good. Now I'm already 45 minutes in. I really need to get to the implementation because that's the fun part or the interesting part. For us, it wasn't that much fun. It was interesting, but a lot of work. Okay, so from theory to practice. The first thing is we're not in the US, right? So we need data sets for Canada or wherever you are actually. There are probably a lot of people who are neither in the US nor in Canada that want to benefit from this kind of technology. And so for Canada, there's actually already a published data set, the HYSETS data set. That's also for academic use primarily. That includes a lot of streamflow records, a lot of these basin attributes like slope, topography, land cover, all this sort of stuff. Also global precipitation data sets. And this is a very good point to get started. So HydroAtlas is actually global and they have a lot of data. And this HYSETS data set is sort of a augmented Canadian version of that. And that was very useful for us for our initial testing. But it's good for a first cut. It's not sufficient for operational use. So this is sort of the Southern Ontario region where we've been doing forecasts already with our physical model. And the red dots is where the watersheds where HYSETS actually has data. So it's not much. And this is not useful for forecasting, right? So if you're taking an academic study and want to operationalize this, usually you have to really work on the data and the coverage. And we've added more watersheds. All the blue dots are now gauges that we added. And most of these are at locations where there are actual stream gauges so that we can validate. But I want to point out here that we can actually add synthetic gauges at any point along a river as well. And we have the infrastructure for that. And so if somebody needs a streamflow forecast where there is no gauge, like this is actually possible. But this is the kind of thing that you need to understand what you're doing. You need to understand sort of how this works, and then you can provide that service that's more useful to an end user rather than looking at just what is published in an academic paper, right? And so making this extra step is, I think, something where there's really a room for startups and the sort of climate services businesses to make a difference. Another thing is augmenting the precipitation data. The rain data in the prairies is actually very poor because it doesn't include radar data. So we are adding that right now to increase the skill. Okay, so a lot of data augmentation that's necessary. Right? And yeah, then we train models in Canada, and we are getting pretty good skills. So on the right-hand side is the distribution of our skill. It's 0.65. So the Kratset group in the US got higher skill, so almost 0.8. But that's actually largely because the data in the US is better than in Canada. So in Canada, we have a lot of gaps, especially in winter, because gauges freeze. And the precipitation data is not of very high quality, just because it's a very large country, right? So yeah, but in some areas we get really good skill. The prairies tend to be the worst. And there's this saying, and that actually dates back to conceptual rainfall runoff models, that the prairies are where hydrological models go to die. It is very difficult to get good skill there. Yeah, we're still working on that. Interesting observations. The models don't always work perfectly. If we only train models on Ontario, for example, you would think that maybe they are more specialized, so they should work better in Ontario. But this is actually not the case. The performance is actually worse. So models that are trained over all of Canada or in parts of the US perform better, even in Ontario, even though that might seem counterintuitive. And another thing that we've noticed is that, and this relates to the precipitation data I mentioned before, when we see poor performance, it's often because the model misses precipitation events or fails to translate an apparent precipitation event into a runoff event. And that is because the training data for precipitation is actually not very good, and the precipitation data itself actually misses a lot of events. And there are specific reasons why this is the case, and you kind of need to understand some of the metrology to know why this is the case, but it's not very surprising that this happens. So domain knowledge here is really helpful. Okay, so then how do we get to an actual forecast? So this on the right-hand side is an actual forecast that we are generating. We have the watershed data assembled. We have the ML models trained, but then, yeah, we have to return to this conceptual diagram. We have a delivery platform, like a website. We have the physiography of the watersheds, but now we do need to look at the weather forecast. So you remember this slide? The weather forecast, the weather is essentially what drives the hydrology, right? So we can only simulate the hydrologic response to a weather scenario. And so we have to assume that we know the weather, and we don't really know it, but we just substitute in a weather forecast and like a gridded numerical weather forecast, and just assume that we know that this is the right weather. And then we compute the hydrological response with our machine learning model. And that works reasonably well, but of course, it also depends on how good the weather forecast is. And we use weather forecasts from the Meteorological Service of Canada, Environment Canada. And what we use is the Global Ensemble Prediction System. So it's also called GEPS. Okay, good. And the process of getting these weather forecasts into the machine learning forecast is actually quite involved. And I just want to illustrate this here. It's not particularly sexy, but this is a large part of the work. And so I do want to honor it with a slide. And so there's real-time data on the left-hand side. And there's also the static data and also historical data on the right-hand side that I've already talked a bit about. And so first, we need to download daily weather forecast. This process needs to be automated. This is like a few hundred megabytes typically to a few gigabytes that you need to download and gridded binary data. Then we need to extract that from their gridded binary format. And so we need to be able to read and understand that. And this is, of course, also all automated. We need to compute the variables that we need to force or to drive the machine learning models. So a lot of pre-processing is necessary. We need to aggregate that over watershed areas. So yet another pre-processing step. Then we do need observational data, both static characteristics, but also historical weather to spin up the models, right? They have a memory cell, an internal state, so that needs to be spun up. And I'm mostly glossing over that because that's also a quite involved process. Then we need to merge that with the weather forecast. And then we can finally run our forecast, right? So there's a lot of infrastructure and process that goes into this, and this is very technical. So it sounds conceptually very simple, and when you read a paper and you think, oh, okay, like these machine learning models are awesome, and we can do streamflow forecasts with that, yeah, there's a lot of steps you need to do before you can actually make a useful forecast with that. Okay, and so we have this forecasting platform. We already had a large part of the weather data processing implemented for our physical model, but there are, of course, important differences. We also sort of have a modeling pipeline set up, and we do have a delivery platform where you can like go on the website, you can like click on a balloon, and you get a forecast. So that part was already there as well. And if we had to do all of this from scratch, this would have been a much larger undertaking. And so I'll just show you some examples. So we do have this deployed now on our experimental platform in Southern Ontario, and we're also adding more parts of Canada. So we have about 1,600 stations across Canada now, highest density in Southern Ontario at the moment. And so we can just click on one of those balloons, and then we get a station. This is the Payne River near Ottawa. We have the real-time historical observed data over April. So this is recent, so over April here. And then you have a forecast that's initialized here on the 25th. And then, so I chose one that's a little bit back so you can see a little bit of the overlap with the observations. I pulled this yesterday. And this is what the machine learning model predicts. So it looks like a reasonable prediction. But it's not always that good. So sometimes we also miss an event. So this is from 2 weeks earlier. This event was mostly missed by the forecast. The reason was actually that this was mostly missed by the weather forecast, or it was sort of at the low probability end of the weather forecast. as you can see sort of from this spread of the ensemble. So the red line is like the median, and then these are forecast percentiles, so it's probabilistic. Right? So the weather forecast is a limitation in this kind of forecasting. If the weather forecast is wrong, our forecast is wrong too. Yeah. There are other problems like the initialization, for example. So we're still working on this. And this has to do with the spin up and the precipitation data that I mentioned earlier. So the models do not always initialize correctly. So sometimes based on the previous precipitation data, which may have been not quite correct, the model assumed that the current flow would be higher, and it's not corrected towards the current flow. So the model, this model forecast has never seen the observations here, right? So it doesn't actually know what the current conditions are. And so considering that, it's actually a pretty good forecast. But there's room for improvement here that we are currently working on. So data integration, right? And just for completeness, I also want to mention, we also have a physical model forecast here in the same watershed, and this is the same forecast. For the physical model, we have a little bit more sophisticated initialization. So that's why it looks much better in the beginning. This model also requires a lot more calibration, and it's driven by HydroSphere, our physical model. Okay, good. So I just want to summarize with some closing thoughts. This is essentially the end of the presentation. It should be clear that a lot of the impacts of climate change manifests through hydrological or hydroclimatological extremes like flood and drought, and those are just the two end members of the hydrological cycle. And machine learning can actually be a really powerful tool for environmental prediction. But you do need to understand the problem, and you need to know what has been done before so that you understand the strengths and the weaknesses, and you don't try to reinvent the wheel, right? There are, in successful machine learning applications, there are specific reasons why they are successful. And often people have developed methods in the past before that have been handcrafted and that actually work quite well. And it is really important to learn from that and not ignore that. It is also extremely important to know the data ecosystem in your domain. And this requires some domain knowledge. So you have to know what kind of data are available, where to get data from, where to get the weather data, for example, how to interpret the weather data, and to know what the strengths and weaknesses of these data sets are. This is really important. So, for example, a lot of the weaknesses we are seeing in the models now have to do with weaknesses in the data in Canada. And because we do have some domain knowledge, we also have some ideas on how to fix that. It's not the model architecture here. But then maybe the most important point here is demonstrating the skill in a research setting is one thing, but translating this into an operational setting is something entirely different. And it requires a lot of infrastructure. And you, as I said before, you need to do a lot of work to augment the data. And then you need to also use these numerical weather forecasts that are really at the center. And there are also machine learning approaches for that. But as I mentioned, this is a different topic. Okay. And so with that, I just want to leave you with a fun animation. And this is actually not a machine learning model. This is a physical model that my colleagues made. This is from a large flood in Alberta in 2013. Some of you may have heard about this. Medicine Head. This was it's mainly driven a rain on snow event, caused a lot of damage. This would have been easily predictable. Yeah. So maybe we can just go over this one more time again. And there were a lot of sort of structural problems and administrative failures here, and policy failures. Why this was such a disaster? This was not necessary. We would have been able to predict this, but it wasn't predicted for other reasons. Very sad case. Okay, and so I'm at the end now. I want to thank the team at Aquantia, of course, for doing all the implementation work. But I also want to thank the Ontario Water Consortium, who supported us with a grant for industrial research that really made it possible for us to dive into this and spend some time investigating how to make these forecasts happen in an operational environment. Without that, it would not have been possible. If we had to chase grant money or do consulting projects instead, we would not have had the time to really dive into this. So this was really instrumental as well. So thanks to the Ontario Water Consortium. And with that, I'm done, and I'm happy to take questions. And I realize I've actually talked for an hour.